Ooh, I didn't want to do that. All right, so Newton's third law. A force is a push or a pull that acts upon an object as a result of its interaction with other objects. Forces result from interactions. Now, does there have to be like physical contact for there to be a force applied? No? Like if I want to like push the table, don't I have to?
Gravity's not a physical.
Oh, to blow on it, like if there's wind. Okay.
Push the balloon up.
Let me get to that one. But if the wind, like, doesn't the wind consist of like the air, which is like air, oxygen, and nitrogen molecules pushing against something, doesn't it? You guys are saying what? Gravity. Oh, what about gravity?
Force.
Gravity's a force? And what? There's no contact. Absolutely, you're right. That's when I drop the tennis ball. Sure. Make sure you have lock. Plug them in when you're done. Bring it back. All right, I'll just wait. As discussed in lesson 2, some forces result from contact interactions where there's actually a physical contact. Things like the normal force, frictional force, tensional forces, applied forces, pushes and pulls are all examples of that. And you don't need to worry about the fact that maybe some of those are little contact interactions, what I wanted. Are a little bit, maybe you're not sure about, right? Other forces are the result of action at a distance interactions. Gravitational, electrical, magnetic forces, right? Action at a distance, there is no contact. And when we get into the gravitational fields unit, we'll discuss that in further detail. For now, all you really need to know is that some forces can be pushes or pulls, physical touches, and others can be non-contact like gravity. Okay. According to Newton, whenever objects A and B interact with each other, they exert forces upon each other. When you sit in your chair, your body exerts a downward force on the chair, and the chair exerts an upward force on your body. There are two forces resulting from this interaction, a force on the chair and a force on your body. Excuse me. And I also want to make a note that there's two forces and there's also two objects. Two forces, two objects. Every single time. One force per object, you could say, right? Okay? These two forces are called action and reaction forces, and are the subject of Newton's third law of motion. Formally stated, Newton's third law is, for every action force, there is a equal and opposite reaction force. And you probably have been told this law if you know it. But the question is, do you believe it and do you understand what it means? And that's my job today, is to get you to go beyond just giving me the words back and regurgitating it and truly understanding what it means. My guess is that some of you don't even realize that you don't believe it. Because I've been through this little rant before. This statement means that in every interaction there is a pair of forces acting on the, again, two interacting objects. The size of the force on the first equals the size of the force on the second object. When I say equal, I mean they are the same. If one's 50, other one's 50. The direction of the force on the first object is opposite to the direction of the force on the second object. Forces always come in pairs, equal, there it is again, and opposite action-reaction force pairs. Okay. Do you believe it? Yeah? Can you apply it? Here are some examples. A variety of action-reaction force pairs are evident in nature. Consider the propulsion of a fish through water. Right? How do fishes swim? They wiggle their tail. Right? A fish uses its fins to push water backwards, but a push on the water will only serve to accelerate the water. Right? If the fish pushes on the water, well, then the water does what? Goes backwards. That doesn't make the fish go forward. But a push on the water will only serve to accelerate the water. Since forces result from mutual interactions, the water must also be pushing the fish forwards, propelling the fish to the water. So the water pushes. The fish pushes on the water, and the water pushes back. The size of the force of the water equals the size of the force of the fish, right? Equal. The direction of the force in the water backwards is opposite the direction of the force in the fish forwards. For every action, there is an equal in size and opposite in direction reaction force. Action, reaction, force pairs make it possible for the fish to swim. Clear as mud, right? Clickers are coming. Consider the flying motion of birds. A bird flies by use of its wings. The wings of a bird push air downwards. Since forces result from mutual interactions, the air must also be pushing the bird upwards, right? Bird flaps its wings, pushes air down. Air does what? Pushes bird up. How come I can't do it? What do you mean I'm too heavy? My wings don't have a big enough surface area. If I flap faster, maybe. I'm not pushing down enough air. Let's go back to what Adam said. What'd you say? I'm too heavy. I have too much mass. So are you saying that I can't generate enough force to reach that? The size of the force on the air equals the size of the force on the bird. The direction of the force on the air downwards is opposite the direction of the force on the bird, which of course is upwards. For every action, there is a equal in size and opposite in direction. I feel like I'm repeating myself. I feel like I'm repeating myself. Especially since I did it already this morning. Action-reaction force pairs make it possible for birds to fly. Every afternoon, I feel like I'm watching a rerun, except I'm the one that's doing the speaking. Consider the motion of a car on the way to school. The car is equipped with wheels. You might be familiar with that. They spin. As the wheels spin, they grip the road and literally push the road backwards. Since forces result from mutual interactions, the road must also be pushing the wheels forward. The size of the force in the road, what do you know? It equals the size of the force on the wheels of the car. The direction of the force in the road backwards is opposite the direction of the force on the wheels forward. For every action, there is a, I've said it a few times, equal and opposite. I'm going to walk across the room. Watch me. Pretty exciting, eh? How did I do that? I push the floor back, so you're saying that as I'm walking, I'm pushing the floor backwards. And then the floor pushes me forward. So how come if, was anyone walking after school yesterday outside? When it was crazy, super slippery? Yeah? Okay, and I went out, about 5 o'clock, I left school, I went, the front pad, it's really smooth. It was like curling ice, right? So, yeah. So, what happens then? If you try to walk on that, right? How come I can do it now? Less friction, right? So, it's actually friction, as I push back, right? Friction does what? It pushes me forward. With the same amount of force? Equal. Same amount of force. How come I move forward but the floor doesn't move backwards? It's bigger, way bigger. Look how big it is. And it's attached to the walls. Action-reaction force pairs make it possible for cars to move along a roadway surface. Okay. Are you ready? Come get a clicker. Are you nervous? No. I'm a little bit. I got butterflies in my stomach. Come on. How many times did I say equal? Well, see, here's the part where I said you can say it, but you don't believe it. You don't get it. My job today is to get to that point. Listen carefully. Jay asked, how come the bus keeps moving? How come the dragonfly gets stuck? Giant mass. The bus is massive compared to the bug. F equals ma. Big giant mass, little tiny a. Little tiny M, big giant A. Is that funny? For every action, there is a equal. I can't emphasize that enough. The fact that the firefly splatters only means that with its smaller mass, it is less able to withstand the larger acceleration resulting from the interaction. Besides, fireflies have guts, and bug guts have a tendency to be splatterable. Windshields don't splatter, they're solid. Okay? The forces are the same. Braden, what are you doing? Why do you have your laptop open then? You don't. Question 2. For years, space travel was believed to be impossible because there was nothing that rockets could push off of in space in order to provide the propulsion necessary to accelerate. The inability of a rocket to provide propulsion is because, so think about this, right? If I'm on like rollerblades and I push on here, right? What do? I go sliding backwards, right? What if I'm just on rollerblades and I go?
You'll like.
Will I go backwards?
No.
Okay, so this inability of a rocket to provide propulsion is because, listen carefully, space is void of air, so the rockets have nothing to push off of. B, gravity is absent in space. C, space is void of air, so there is no air resistance in space. Or D, nonsense, rockets do accelerate in space. Sorry, and I've been able to do so for a long time. A, B, C, or D. Feel free to think about it for a second. Well, I need to start it, don't I? Correct answer is D. It's a common misconception that rockets are unable to accelerate in space. The fact is that rockets do accelerate. There is indeed nothing for rockets to push off of in space, at least nothing which is external to the rocket. That's no problem for rockets. Rockets are able to accelerate due to the fact that they burn fuel, push the exhaust gases in a direction, opposite direction, with which they wish to accelerate. Okay. Anybody a hunter? You probably know that when you shoot a gun, there's some recoil. Many people are familiar with the fact that a rifle recoils when fired. This recoil is the result of action-reaction force pairs. A gunpowder explosion creates hot gases that expand outward, allowing the rifle to push forward on the bullet. Consistent with Newton's third law of motion, the bullet pushes backwards upon the rifle. Listen carefully. The acceleration of the recoiling rifle is greater than the acceleration of the bullet, smaller than the acceleration of the bullet, or the same size, i.e. equal, as the acceleration of the bullet. A, B, or C? I have to admit, it is a trick, and I led you a little bit down astray, but it's to make a point. Now, I have said over and over and over, equal, but equal what? Forces. Equal and opposite forces. I did, but to make a point. Wouldn't you rather be tricked today than on a test where it counts for something? Okay, listen carefully. Listen. Here's the learning part. Okay? The force on the rifle equals the force on the bullet. The acceleration depends upon both force and mass. The bullet has a much greater acceleration due to the fact that it has a smaller mass. Probably, maybe 30, 40, 50 times smaller? Remember, acceleration and mass are inversely proportional. Big, giant things have small, tiny accelerations. Small, tiny things have great, big, giant accelerations. And they go really, really fast. Things like bullets. Okay? So what's equal? The forces. What's not equal? Acceleration. You think I'm going to test you on that?
Yep.
You betcha. Okay. In the top picture below, guy's name is? Doesn't look after his money very well. Can't budget. Is pulling upon a rope that is attached to a wall. In the bottom picture, Kent is pulling upon a rope that is attached to an elephant. In each case, the force scale reads 500 newtons. Kent is pulling A with more force when the rope is attached to the wall, or with more force when the rope is attached to the elephant, or the same force in each case. A, B, or C. It's a series of, it's not trick questions, it's questions that make you think. Oh, I gotta start, sure. I'm hoping. Yep, the answer is C, the same force. The scale shows the same, right? The forces are the same forces. Kent is pulling with 500 newtons of force in each case. The rope transmits the force from Kent to the wall or the elephant and vice versa. Since the force of Kent pulling on the wall and the wall pulling on Kent are action-reaction force pairs, they must have equal magnitudes. Inanimate objects such as walls can push and pull. I think there's one more. No, there isn't. Okay. No, it's fine. Okay. So let's have a look at these here. So here's some more learning parts. So put the devices away. Open the ears. Don't worry about marks. Worry about learning something. Number one, an asteroid tumbles through space in a straight line forever. Well, that is clearly number one. Objects in motion stay in motion. Now, pretty much everywhere there is some form of gravity, which means it doesn't go in an entirely straight line. In fact, it travels in a big orbit, right? Like comets come by like every 86 years kind of thing, right? Halley's Comet. Right? They take big, giant orbits, right? But more or less, it's a giant straight line. One number two now. You and a friend are at ice skates. You push her, and you both move in opposite directions. So that would be third law. Action, reaction. Right? Are the forces the same? What? Yeah, I had a phone call this morning. The phone call was, "Can you come to Karina's for breakfast?" Yeah, that's why you don't need to answer.
I didn't know.
Yeah, well, if you don't know, then it's not that important.
Sorry. Last time I was a guy from work.
Yeah? I'm sure you have wisdom. No?
Maybe.
I think everyone's got a little bit of wisdom. Or not even can. Okay, what I want to ask is, what if one of these people is bigger than the other? What happens? The small one goes further, right? The small one goes further. Okay, number three, you drop your books in the hall while running. Your books slide down the hall until they slow to a stop. First one, so stay in motion. Unless, back to the outside force. So in this case, the outside force is friction. Outside force is friction. Opposite motion, stay in motion, unless they're acted upon by outside force. Yeah, that's true. While making a snowman, you make a really big snowball. You push the ball really hard, but it only accelerates a little. Second law. Large objects, small acceleration. Small object, big acceleration. Can't wait to show you guys do.
The acceleration and then
Pardon me?
acceleration.
Yeah, it's kind of cool. Number five, hunters typically get a bruise on their shoulders after firing a shotgun several times. Zach says three. Hunters typically get a bruise on their shoulder after firing a shotgun. So that's three. I had one person this morning argue number two. You want to say number two? Number two is the large mass, low acceleration. Small mass, big acceleration. Yeah, it's the bullet. The bullet gets accelerated, right? Does the person's shoulder get accelerated back? A little bit, right? But it's you are more massive than the bullet, so you don't go back as far. You just get a bruise as opposed to flying through the air. Let's get our Number six, a car is driving in the rain and trapped water under the tires. What do they call that? Hydroplane. Waterboarding is torture.
Water.
Is that like surfing on the road?
That's what my.
Are you okay with waterboarding? Yeah, that sounds fun.
No, we don't have to fun anymore.
Bumper shine. I'll keep calling you. Anyways, when the brakes are applied, the car still won't stop. One? Why one?
Because objects are in motion,
Stay in motion unless acted upon by outside forces, because your hydroplane, there's no friction, there's no type. Done. Okay, number 7 is just the word friction. I always struggle with this one every year. Or, there is no Newton's fourth law. What, all of them? Explain that. Well, that's true, right? Well, action, let's go to the first law, right? The object in motion is the outside force. The outside force is always friction. The mass acceleration one, yeah. Action, reaction, well, okay, if you like just walking down the street, right? It's friction that pushed you forward. So I would go with 1 and 3. If everyone in the world ran east at the same time, the world would stop spinning. 3? Action, reaction? 1? It would be the outside force. Yeah. Most people say 3, right? Action, reaction, but one I'll take down. Now, would this really work?
No.
More 3, action, reaction. Okay. Well, let's just talk about this for a second, because I got some time, right? Which way does the Earth actually spin? Does it go this way? Or does it go, or does it kind of switch back and forth day to day? Like this? Okay, which way does it go? Well, we know that the sun, not to scale, right? The sun comes up in the east, which of course is over here, right? So the sun does the sun do this?
No.
No, the sun stays here, and we do this, right? Okay, so if the sun comes up in the east, then we would have to spin which way? We have to spin this way, right? Right, because it goes across it, so it would be like this. Okay, so the Earth is spinning this way. So if you're running east, then you're pushing west. So if I'm spinning like this and I push west, then yeah, it would slow it down, wouldn't it? But exactly. Big, giant, crazy, massive mass. Exactly the same thing as people jumping, okay? Would it work at all? No. Not even if you had the baby. Okay, what's the next question?
If the world stops spinning, the ocean would go on the land.
The oceans and everything, and then there's all that.
I still think, look, well, if you think about that, Anna, okay, so Anna says, what if there was a person on every square inch of surface, including the ocean?
No.
Still, all you would do, like, look at this is to scale. Look at how wide Canada is. So how tall is this layer of people on here? Like atomic size, right?
Yeah. Everything is
Exactly. Unfathomable, more massive. We don't understand. Okay, so now the next question is, if the world stops spinning, the oceans would spill onto the land, killing us all. There's your happy thought for the day.
3 and 1.
3 and 1. Explain now.
3
The objects of motion? Yeah, exactly, right? If the world is spinning, the water is spinning with it, but then if you stopped it, the water would keep spinning, and who would get it first, BC or Newfoundland? Who would get the water first? BC?
Yeah, it would be.
Right? Because we're spinning this way, and then which way is the water spinning? And then you stop the water. So yeah, BC would get it first. We got a few minutes before it got here.
Is that
No, it would never do that.
Would the water do that? Yeah.
But it would hit the rock.
Well, that's true. What is the rock? Do you know how much water there is over here?
Yeah, but is all of it like?
Do you know how much water there is over here?
And like, when is the world ever going to stop?
Well, you have to figure out how fast is the world actually spinning, and the speed, and you have to know the distance between us and the ocean, and then I'm thinking,
We'd be able to see it coming.
yeah,
If they,
you look out to Saskatchewan and see it coming.
if it
I'm thinking minutes, Danielle. I'll work that out.
That's not fair.
I'll work that out.
what if the world explodes?
One is obviously, yeah, the water in motion, right? And Josh, you said three as well, action reaction? Well, they're killing us all, I guess, would be the Alright, last one. Last one. A powerful explosion that sends smoke materials flying at very fast speeds. Clearly two, exactly. Clearly two. Small materials, small mass, big speed. Small mass, big speed. Okay, I got a couple videos to show you.